Okay, I apologize. I got cut off there for some reason. So the result is that I want to claim is that these two programs are equivalent, and you could prove that because what does it mean? That it means that no matter what state I start in, this program can arrive at the same state as this program. So no matter for every, well, the definition of S1 being equivalent to S2 is that for every S and S prime, S1 comma S goes in some number of steps to S prime if and only if S2 in state S can also go in 0 or more steps to S prime. So that's what it means for two programs to be equal. And so you can look at each one of these paths here and you could say, okay, in the path over here where this program here finally evaluates down. First, we evaluate the x equals 0, and we get back this state, and then we evaluate the x equals 1, and then we evaluate the x equals 1 plus 2 is 3, so we end up in this state. Well, that's easy in the OR to just select the second one, and then the second one, and then evaluate it. The other possibility for this program up here is that first we evaluate this part, we evaluate and we get S, it gets to 1, and then we evaluate this part, so now we get S has, where X has this value 0 here, and then finally we evaluate X gets the value of X plus 2, so now we have X having the value 2, and then here is the one where we evaluate first. We're in the state where we've already evaluated X going to 1, and now we evaluate this part and we get back, okay, X goes to 3, but then we still have this left over, which smashes it away, the whole result, and sets it to 0. And so in that case, we can use the OR rules to select this one. So this is the section on concurrency. It's not it's not very useful without some kind of semaphore or mutual exclusion operator. We can't really write any very interesting programs in this, but it does introduce non-determinism, and it illustrates kind of the complexity of concurrency. Now, I thought I'd do problem 5.2 from the book, and if you want to try it yourself, actually, I'm going to ask you to do it because I did it one way and then I realized, oh, there's another way to do it. Let's do it a different way. So I'm going to ask you as a homework to do problem 5.2 in a different way from this. So my first idea was this. So the idea is to say, okay, look, suggest an alternative small step semantics for PAR that allows both S1 and S2 to make progress. So the first rule that I thought of is, okay, look, what we do is we're starting with this in state S. So run S1 from state S and see where you get. And then run S2 and also from the same starting state S, and then see where you get. And then I made this rather complicated union operator here to glue the states back together and to non-deterministically essentially forget, like if S1 and both S2 set X, one of them is S1, let's see if I can show you what I have in mind here. Suppose that I want to evaluate X gets the value of 0, par X gets the value of 1, comma S. And so what I'm going to do is I'm going to essentially, when I evaluate S1, when I evaluate this S1, I'm going to get to a new state that has, so if I evaluate the S1 on the upper branch, I get it to a new state that has S where X has the value 0. But I could also do on the upper branch, I could say X, if I'm going to really make it match the branch, I can't have this. I'm trying to build a little proof tree here to show you how this rule would work, and it's that X gets the value of 0, par X gets the value of 1, comma S, and what would that evaluate to? So there's my, it's so short I can just rewrite it now more compactly. I got S1 in S evaluates to S where X has the value 0 in the state, evaluates to the state, which is a function, evaluates to a function where X, if I give it the input X, it returns 0. And then this one, X gets the value of 1, and also in the original S, yields S gives back the X that evaluates to 1. And so then, if I call this one here S prime, and I call this one here S double prime, then I said, okay, this evaluates to S prime with this funny plus union operator, S double prime. And so what I meant to do with this, what my idea to do with this was to munge the state so that it really only has one of the values, either 0 or 1. Now, how can I do that? Well, I said, okay, look here, S plus union S prime is choose variables X, and then let the value that goes with that be the result of applying S to X and applying S prime, this one, to X. And so then choose would non-deterministically choose the thing. So first I got to tell you, then I'm like, okay, well, what does this mean? And so I say, okay, look, you can write S down arrow X to mean S of X is defined. In other words, there's some K that when I apply S to X, I get K. So S applied to X and S prime applied to Y. So this is a slight generalization because up here they're both applied to X, but is the following. It says, first, what is this set? Well, it's either empty if neither X or Y, neither X is defined for S. So if this is not defined and this is not defined, then you get back the empty set. If it's defined for 1, let's say, that should be a prime in there somehow. The prime disappeared. S prime Y is equal to K, but S is not defined for X, then you just get back K. And if S prime is not defined for Y, then you get back, but S is defined for X is equal to K, then you get back K. And if S applied, in the last case, if S is applied to X equals J and S prime applied to Y is equal to K, you get both those things in there. Now choose is a function, is not a function. Well, choose is some function from the subsets of n. So this is really generalized. Up here we only need 2. So remember, this is the power set. So rho of Z is defined as this. It's a set of all y's such that y is some subset of x. So rho of x is all the y's that are subsets of x. So rho of ints is the set of all subsets of ints, because remember, our partial valuations may not be defined for some inputs. So choose, you can think of it as a function from rho of Z, and really you could think of this as like a total function. So choice is a partial function. Well, I'm just going to say now it could be total from subsets of Z to Z, because we can leave out all the things that are not defined. And that's essentially what we're doing here. So the definition says, look, if X is some subset of the integers, choose X is equal to V. If it is equal to V, that implies that V must be an X. Well, so what does that mean? Well, that means it's certainly, if X is empty, that means there's nothing in X, so choose X can't be defined if X is empty, and that's what this line says here. And choose a singleton, well, that's easy. You just have to prove the one thing, and then it is the case that K is in the singleton set K. And then choose of a 2-element set, JK is either equal to J, X, or choose JK is equal to K. So you have to remember exclusive or. Exclusive or says that, well, one way to think of it is that P exclusive or true, Q is true if and only if P is not equal to Q. Because in the equals case, they're either both true or they're both false. And what we really want is only one to be true or false. So these are the true cases. You can look at the truth table here. This one's false because both of them are true. You know, in the ordinary P or Q, this one would be true, 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 false. And we wanted to, you know, kind of eliminate that case and have just these two be true. So that's exclusive or, is when just these two are true. And so this one is basically saying, look, we don't know which one it is, but choose one or the other. It must be one or the other. Now, this is a lot of elaborate setup to kind of like make this operator on functions here. I'm making this union operator on functions. Now, the first thing I think of is those that, I need more rules, because suppose that S2 evaluates to a single thing, or suppose that S1 evaluates to a single thing. So I fix those up, so add those rules. And then it's also possible they both, S1 and S2, evaluate to individual states. And so then this is going to be an individual state. And so this is one kind of parallel rule that these set of rules would allow you to progress down any branch, but there's a problem here. I mean, this works. This is a perfectly sensible semantics. The only problem is you don't know. It's erased some information, this union operator that I created here, because you don't know which of, it's combining S, what it's doing is it's building a new function that looks like S prime and looks like S double prime, but it mixes together any overlapping spots in kind of a random way. So for these, double entries, that's missing a bracket there. But for this, it's saying, look, apply S to X and apply, and that's this S, and apply S prime also to X, and that's S prime. So what if, we don't have an operator right now, but what if we had like a multiple assignment operator? What if we had some kind of notation that looked like X comma Y gets the value of, 1 comma X plus 2. We could have some kind of parallel assignment operator. Well, this union operator would allow you to have a program that was like this one, par X comma Y colon equals 0 comma 0. And the semantics I'm thinking of is that this means, okay, you evaluate this and you evaluate those two. So let's see, all right, we can write down a semantic. X comma Y gets the value of A1 comma A2 in state S, evaluates to state S, where X gets the value V1 and Y gets the value V2 if S says A1 evaluates in the arithmetic language to V1 and S says A2 in the arithmetic language evaluates to V2. So now if I did this, I'm going to get back this par thing. I'm going to, with a parallel rule, could lead to I need to clean this up a little bit to actually evaluate it. Let's see. Okay. evaluate to? Well, it would evaluate to, let's say, S prime plus union S double prime. But what is S prime? S prime is equal to S, where X gets the value of 1, and Y gets the value of whatever the old S of X was, plus 2. Now, S double prime, so this it would be my S prime would be the answer for this one, and S double prime is the answer for this one. So what is my S double prime? That is also S, but this time where X goes to 0 and Y goes to 0. So here's a parallel assignment operator. Now, the union of these two could choose in one case, well, I didn't mean to erase, could choose in one case that, okay, X goes to 1, oh, and for Y, Y goes to 0. So that's an interesting problem here, where this solution doesn't work in the presence of a parallel assignment operator. So if we go back to the beginning, though, and it says, okay, look, the semantics of par are supposed to be the interleaving evaluation of statements S1 and S2. In other words, you can execute the statements from S2, S1 in any order, as many of them as you want, and then as many from S2 as you want, and then as many from S1 and S2, and then S2. So all if you think of, it's sometimes called like a complete shuffle. You're kind of like all possible orderings are included in there. So if we go down here and you want to solve this problem, another way would be to, and this is all I'm going to say about this, but another way would be to start this one in S prime. And then get rid of this operator and just have it be S double prime. Now, if you did that, that's the same as doing S1 first and then something from S2. Now you're going to need more rules to make this work for all possible cases. So that's my hint, and so I'd like you to do problem 5.2. Okay. Oh, one final thing is that, these partial functions cause interesting side effects that, like, I wasn't aware of. For example, I hadn't really thought about this. I said, like, look, suppose you had two variables, X and Y, and Y is not defined in the current state. So it's not, S is not defined, Y is not defined in S. So what happens if we try to look at the statement, X gets the value of Y in S? Well, that should go to the state S, where X goes to V, where V is what you get by evaluating Y. But Y is not assigned. So essentially, if you get to if you get to a state that looks like this, and it doesn't, as long as S doesn't define Y, there's no place to go. There's no place to go because no rule applies for this one. So this is, if it's not the case that y is defined in S, then that implies this must be in T, I guess I could say. There is no rule applies. That was interesting to me. Okay. It's like an abort. You can't go anywhere. All right. Thanks so much for listening, and you might want to get to work on problem 5.2 with a better solution than my first try. My first try is, first of all, a bit complicated, but also wouldn't work in the presence of a parallel assignment because you kind of mix and match parts of the updated state. Okay, thanks.